Hey everyone, this is lesson 841, a special ratio. Up until this point, we've gone over polygons. We've talked about angles and areas of different polygons. Obviously, we didn't talk about every single polygon because really there's an infinite number of possible sides a polygon could have. So since that's the case, we start to wonder what is it that we can notice about area and perimeter as the number of sides grows in a regular polygon. All right, so what does a polygon with infinite sides look like? What is the area of that shape? What is the perimeter of that shape? And so we're going to specifically look at regular polygons with a radius of 1. So that means the distance from the center to one of the vertices would have a measurement of 1. Right? So every single one of these is going to have that same measurement. The only thing that's going to change is the number of sides in that shape. All right, so usually we would do this activity in class and we would calculate these together, but we're going to skip that process in this lesson. I'm just going to show you what the areas and perimeters would look like for each of these polygons given these number of sides. All right, so as a reminder, I've included a little visual of some of our common polygons, so you can kind of see what they look like as the number of sides grow. And so I didn't draw out all of them, but I think there's enough here to kind of give you an idea of what I want you to see. Now, okay, so here we have a table of values. At the top are the number of sides. So 5 sides would be our pentagon, 8 sides would be our octagon. We have 9 sides, which is our nonagon. All right, so we have some of them drawn out for us just so you can visually see that. But for the most part, I've included 3 sides, 4, 5, 6, 7, 8, 9. And dodecagon is not 10, this is going to be 12. All right, so you can see the number of sides are increasing. So I wanted you to see it visually, and I also wanted you to see the area and perimeter of these shapes as well. All right, so if we calculate the area of the pentagon, right, the pentagon, if we calculate the area of pentagon, assuming it has a radius of 1, we would get a value of approximately 2.38. And if we calculated the perimeter of that shape, it would be about 5.88. Okay, so you might assume, most students assume, that if you increase the number of sides, then the area is going to increase, the perimeter is going to increase. Okay, well, then that means if I put, let's say, an octagon, then the area should be greater and the perimeter should be greater, which it looks, hopefully you can see, there was an increase, right? So that's starting to make sense. So I've increased it 3 sides and there was a little bit of an increase. I've increased it 1 side to 9, and you can see it's a tiny little bit of an increase on both of those. So you would imagine if we start to add a lot of sides, we should see a very big increase. Maybe even double, triple. So as we go through this table, you'll notice there's a bigger increase with the smaller sides. But once we get to let's say 10 sides, and we jump to 15, this is an increase of 5 sides. And you'll notice it did increase, but not by much. And so let's increase it a lot more. So from 15 to 30, we're increasing this by 15 sides. We're literally doubling the number of sides, right? Which is pretty much what we did from 5 to 10. We doubled it, and it went from 2.38 to 2.93. Now, we went from 15 to 30, and you'll notice it got bigger, but not by much. Still not by much. And so, all right, let's double it again. So we added another 30 to 30, and we got 60. For sure, we should see a bigger increase. And you'll notice the increase is even smaller, right? These numbers are almost the same. And from 60 to 90, we increase another 30. And you'll notice that increase is even smaller, right? So it's increasing, but by such a little amount that it's starting to look like the same number. Now, this last one, you'll notice we go from 90 to 180. We've literally doubled 90 sides, and we end up with pretty much the same area. So it's increasing, but by so little bit that these first three numbers, at least the first three numbers, are not changing at all. Okay, so if I double this number, 180, maybe if I put 360, what is it going to change, right? So a lot of times some people think, well, yeah, it's probably going to go up just like a little bit. Well, we test this out, right? We test this out, and you'll notice that once you go beyond these measurements, beyond 90 and 180, which really could be a million sides, it could be 10 million sides. For us, we're looking at maybe an infinite number of sides. What do you think that number is going to be? Well, this pattern tells us we're kind of reaching our limit here. So the area is not going to go much past 3.14 for infinite number of sides. Okay, so then if we do the same thing with perimeter, we'll notice the same pattern with perimeter. It is increasing with the number of sides, but it starts to slow down. Even around 30 sides, 30 to 60, those are almost identical. And then beyond that, 60, 90, 180, you'll notice the perimeter doesn't really change much. And so we could imagine if it has an infinite number of sides, that we're going to end up at approximately 6.28. All right. Now, why is it that these shapes, once they have so many sides, that the area doesn't change much and the perimeter doesn't change much? Okay, so we want to see what we notice. Now, in addition to this table, I've given you some pictures for a reason. Really because I want to ask one question, and that is, what do you notice about these pictures as we increase the number of sides, right? How is it changing? The triangle has very sharp edges, right? Even a square sometimes. As soon as we start to add, we're at 5, 6, 7, 8, 9, this shape starts to change and starts to resemble what? Right? What does it start to resemble? What is a shape with 100 sides going to look like? I think some of us have already seen that. And what is it going to look like if it has 1,000,000 sides? All right. So let's write down some things that we notice. So for the area, we notice that 3.1 was kind of our limit, right? So some type of infinitygon, right? We're going to call this an infinitygon. That's an ugly looking infinity. I don't know if I could do a better one. So, oh my goodness. So, all right, good enough. So an infinitygon, which is going to have an infinite number of sides, The area of that one is going to be approximately, it's approximately 3.14, right, units squared. All right, that's an approximation. And we also notice for an infinitygon that the perimeter is approximately 6.28 units. All right, so if you didn't already notice it before, if we compare these two, you'll notice that the perimeter happens to be twice as big as the area. So technically, this is kind of like the same thing as 2 times 3.14, right? All right, so somehow that 3.14 is a magic number for us. And so some of you probably already know this, where I'm headed with this. So this is 3.14 is an approximation for the number pi. Oops. I don't know why sometimes I can't draw this. I need to zoom in. All right, so this would be pi units squared. And for perimeter, this would be the same thing as 2 times pi units. All right, so what we're getting out of this is realizing that the area of this infinitygon is always going to have an area of pi units if the radius is a measurement of 1. So again, this is all assuming that the radius has a length of 1. Now, what shape is this starting to look like? Right. So as we get to an infinitygon, what does it start to resemble? I'm going to see what you tell me on this one. So can you guess what shape I'm talking about? I'm sure most of you can. If we add an infinite number of sides, what is this shape going to look like? Right? If we keep going on this list of regular polygons. All right, if you said circle, you would be correct. All right, so when we talk about an infinitygon, we're really talking about a circle. So these areas and these perimeters we've been discussing is really the area and perimeter of a circle with a radius of 1. All right, so we're going to use that knowledge going forward to see if we could make some more sense of this. All right, so on this next problem, we're looking at area and circumference of a circle. Now, we've talked about area and perimeter of our polygons, but when we're talking about circles, we start to use this term circumference instead of the word perimeter. Right? They pretty much mean the same thing, and so if you describe it as perimeter, that would be fine. But for the most part, as soon as you use the word circumference, that tells me you're talking about a circle. And so area would be the same. So we came up with some method to find the area and perimeter of our polygons. And our method was traditionally focused on the triangles, right? But in this case, we can't have triangles because you'll notice it's curved, right? It's curved, so these are not going to be triangles. So what normally would be something a little bit more complicated has actually gotten a lot easier for us. So the nice part is all circles are similar, right? Every single circle looks the same. There is not one circle that looks different than the other. The only difference is sometimes the radius might change, so the circle will get bigger or smaller, right? So let's look at some calculations that I've already kind of written out for us. So I'm going to look at the circumference of this circle with a radius of 1. This is what we just calculated in the previous problem. So we said the perimeter, right? Perimeter of a polygon, an infinite polygon, had a, or the perimeter was 2 pi. So this measurement around the circle is a measurement of 2 pi. All right, so that's what I have here, 2 pi. And I'm multiplying it by 1 because this is really our linear scale factor, our linear ratio. So if I multiply 2 pi by 1, it gives me 2 pi units, right? So this is our circumference of the circle. Now, if I have another circle with a radius of 3 instead, now what I've noticed is, just like we've done before, if a shape gets larger, right, it's increasing by a linear scale factor or linear ratio and an area ratio. Well, if I'm talking about circumference, I'm talking about perimeter, I'm talking about linear ratio. So if I look at these measurements, 1 and 3, how many times bigger did that radius get? Right? It went from 1 to 3, so it's growing by a scale of 3. Well, since this circle is always going to have a radius of 1, really all I need to know is what this measurement is. So that 3 is the 3 I'm going to put here. So I'm going to take that measurement, I'm going to put 3, and now I have the original circumference, which was 2 pi of the small circle, but I'm going to multiply it by 3 because it got 3 times as long. So what happens when we multiply 2 times 3? We end up with 6 pi. Okay, so 6 pi units. All right, so we've calculated the circumference. We know the circumference of the small circle with the radius 1, and now we just calculated the circumference. So again, circumference is that distance around, and it has a measurement of 6 pi units. If I want to know what that is the decimal, then I could put that in the calculator. It's a lot easier to leave it in terms of pi. It's a lot more exact. All right. And if we look at the areas right below it, I've also set it up for area as well. Now, when we talked about ratios before in a previous lesson, if we know the linear scale factor, then we could use that to figure out the area scale factor. And so the nice thing is we're just going to use this same number. In this case, it's 1 squared, right? So here's that squared to get our area scale factor. And if you remember from the previous page in notes, we said the area was equal to pi, right? 3.14. So 1 squared times 1, or 1 squared is 1, and 1 times pi is pi. So this will give us our area of the small circle, which we already knew that from the previous page of notes. What's new to us is how do we get the area of this circle? Well, if we take the radius, which also happens to be our should be our linear scale, and we square it to get our area scale factor. Right? If we square it to get our area scale factor, then we multiply these. 3 times 3 is 9, and so we're going to be left with 9 pi units squared. All right, so we've taken what we've known about, or we just learned about circles or this infinitygon, and we figured out the area is always going to be 3.14, right? 3.14. And the circumference is always going to be 6.28. This is what we figured out on the previous problem. Now, our goal was to figure out, well, how can I figure out the radius, or how can I use the radius to help me find the circumference and area of this circle? Well, if I take the same measurements from here and I multiply them, if I multiply them by the right scale factor, then it'll give me a new area. All right, so let's verify some ratios that we're familiar with. So ratios of circumference, if I actually take, let's do large over small. So the large circumference was 6 pi over 2 pi, which this should reduce to, right? 6 pi over 2 pi reduces to 3 over 1, which, if we remember correctly, our ratio of areas should be the same ratio of perimeter or sides, but just squared. So is that the case? Well, if I take 9 pi and I divide it by pi, I end up with 9 over 1. All right, so this tells us that our ratios are working out perfectly, which is what we're familiar with on the previous lesson. Now, we'll practice a couple more problems with this. So in general, what we're trying to get is these equations for the area of circle and circumference. So you might have seen these before. So area of a circle is going to be pi r squared. Right? So pi represents that area of radius of 1, and then r squared represents us multiplying by our ratio of areas, and then 2 pi represents the circumference times another scale factor as well. So in this case, r is going to be our radius, which will also be our linear scale. So this should make it a lot easier to find the area and circumference. We don't have to divide it up into triangles. We don't have to do anything fancy. All we need to know is what's the radius of the circle. All right, so here's a couple of examples, some practice problems that I think are worth doing, some common questions. So first one, on the left side, I have a circle with a radius equal to 10. So I'm telling you the radius is equal to 10. I have a picture for us, but the reality is we don't even need the picture. The only information that we truly need is to know the radius. We already have formulas, as I have written above. I've also rewritten them here for us as well. So area is equal to pi r squared, and circumference is equal to 2 pi r. Now, if you're given the radius is equal to 10, then the question for you is, what does the area equal to, and what is the circumference? So I've already worked those out for us. And so I'm going to plug in these numbers. So since radius equals to 10, I'm going to put a 10 here in place of the r, and I'm going to put a 10 here in place of the r for the circumference. All right, so then your task would be to multiply this out and get an answer. So don't forget, area should be units squared and circumference will be units, since it doesn't look like any units were given here. And so I'm going to ask you to calculate this. Let's see if you could type this out. We want not a decimal answer, but an exact answer in terms of pi. What is the area of this circle with a radius of 10? right, if you multiply that out correctly, you should have 10 times 10 is 100, and then you would have pi. All right. If you were writing that out, if you can't write the symbol pi, one method is just if I put 100 pi. Pi is how we write, 100 pi. All right, so pi would represent how we say pi. If you were going to type that out, if you couldn't do the symbol, but I think most calculators or even typewriters, keyboards have a method for you to use the pi symbol if you look for it. All right, and then second question is, what's our circumference? All right, here we're going to multiply 2 times 10, and that would give us 20 pi. All right, we always want to put the pi at the end. So if you put pi 20, that would not be the best form to leave it in. You would have to rearrange it so that the numbers come first. All right. Second question might be given, the information might be given a little bit differently. So in this case, what if I just tell you the diameter is equal to 14? If the diameter is equal to 14, what is the area and what is the circumference? Well, two things. You would need to know what the diameter is. So if you do, then you should be able to tell me what the radius is. If you're not sure what the diameter is, let me remind you. So diameter is, another name for diameter is a chord that goes through the center. All right, so in this case, our diameter would have a measurement. So this is our diameter. And that equals to 14. So diameter has a length of 14. Now radius goes from the center to any point. So it could be from here to here, or it could go from here to here. Right? Any point on the circle could be considered the radius. So the question is, if the diameter is 14, what is the radius of this circle? Well, the shortcut is, well, if this is the center and it goes to the edge, you'll notice is exactly half. Right? So in this case, the radius is going to be 7. Right? So if I draw this in, this would be 7. All right, so the whole goal of this is to figure out what the radius is so that we can plug it into our equations. All right, so I'm going to let you plug that in and tell me what's the area of this circle with diameter equal to 14. All right, so let's see if you got this correct. We're going to plug in a 7 because that's the radius. And 7 times 7 is 49, and we're going to have pi units squared. So if you entered in 49 pi, that would be correct. And what is the circumference of this circle? Circumference being the distance around. So can you tell me what the circumference is of this circle? All right, let's see if you got this correct. We're going to plug in a 7 as well. So we're looking at 2 pi times 7. So 2 times 7 is 14 pi units. All right, so hopefully you got that correct. So this is pretty much what you need to be able to do. If I give you the radius or diameter of any circle, you should be able to tell me the area and circumference of that circle. All right. This will stop right there on this lesson, and in the next lesson, we'll be practicing some more problems using these formulas of area and circumference. Alrighty, let me know if you have any questions.